Hello, everybody, and welcome to Chapter 3 of our demo about using the C++ client with Deephaven. I'm Corey Kosak. I'm here with my colleague, Christian Ferretti.
Hello.
And in this chapter, we are going to talk about one item of unfinished business from before, namely processing modifies, the modify messages from ticking tables. To remind you, previously we talked about ads, how to process ads, and how to process moves, but we deferred talking about processing modifies. We're going to do that now. And we're also going to do a couple of examples of processing larger amounts of data. We're going to target 1 million rows per second, and we're going to show how the C++ client handles that perfectly comfortably. And in the final example, we're going to show some more real-life data where we're going to subscribe to CoinBase and access some ticking data from there. So let's get started. So in our first example, we're going to make a very kind of gentle, kind of simple ticking table on the IDE side. So let me switch to the IDE. As usual, we're going to import the timetable symbol, and we're going to write this query. The job of this query is to tick every second. Upon ticking every second, it's going to add a new row with the int64 value being this kind of monotonically increasing integer that we like to use a lot. And this bucket is that integer mod 10. So it's going to have the effect of going 0 through 9 and then wrapping around because of the modulo 10 through 19 and so on. And then importantly, we're going to do this last by bucket. Of this table we've created, we're only going to keep the last row for a given bucket. And this is very similar to like a group by operation in database theory. So as you can kind of see, it's ticking away 45, 46, 47, and the timestamps are changing every second as well. So if we go back to the C++ side, let's run our trusty program and do the usual steps. First we'll print the whole table every time, and you can see that every second, not the whole table is changing. You can kind of see which row, you can kind of eyeball it and see that the second row, the third row, the fourth row is kind of changing every second. Now we'll use this, let's run this option where we print the diffs, but using library code to print diffs. We won't actually write that code ourselves. Option 2 this time, demo 3. And this is kind of interesting. I'm going to stop this really quickly and scroll up. The way the library is written, once you've subscribed, the first message you get from the server is the message that brings you current. Like you know nothing, so you need a message that kind of brings you to the current state of the world. And that's why we got these ads and these 10 rows telling the client what the current state of the world is. And then subsequent to that, we started getting modify messages. And the way modifies work, the server tells the client which rows were modified and what the new values are. And by the way, the server, in an effort to be efficient, the server gives you that information on a column by column basis. So it might say, oh, for column 1, you had modifies in rows 3, 4, and 5. For column 2, you had modifies in rows 10, 11, and 12, whatever the case may be. So it's not necessarily, the row doesn't necessarily cut across all the columns. It is more like the server tries to like pinpoint exactly on
what changed.
Exactly what changed. Yeah, exactly. So you can see here, so the way the library is rendering this, when it sees a modified row, it prints the row, the value of the cells before the modify and the value of the cells after the modify. And this is kind of for verbose debugging convenience. So you can see here, we got a modify of physical row 0. And the way the library does is it renders these values with little stars around them. So you can say, well, before the timestamp was this thing, ending in 5715. After the timestamp was this thing, ending in 5725. Likewise, before the int value was 110, and after the int value was 120. Just going back to this, going back to the Deephaven IDE for a second, even though it's not, you have to kind of look for it. It's not like highlighted with little stars, but you can see that every second, both the int value and the timestamp are changing. But importantly, the bucket number is not changing. And you can also see that in our C++ code. There's no little star here because the bucket number didn't change. For row 1, the bucket number didn't change, but the timestamp and the int64 value does change. Oh, and so I should show you the code for that. That might be nice. This is our sort of standard calling framework that we always use.
For these demos, right?
For these demos, yeah, for these demos. as usual, the meat is here in callback print diffs, but this callback is pretty simple because it's relying on the library to do everything. And in fact, this is a very comprehensive print diffs. It prints whatever happened to the table, whether it's removes, adds, or modifies. As it happens in this demo, only modifies happened. But if other stuff was happening, we would see it.
We did see the ads at the beginning, though.
Oh, right. Oh, you're right. Good point. So great point. So, so that would have been this clause here. But basically, when one of these things happen, you're basically just calling to one of our little stream methods that takes these little flags are, do you want column headers? Do you want sort of physical row numbers for debugging purposes? And you just tell it what table you're talking about, what the row sequence is of the modified rows, and it kind of handles the rest of it. We talked in detail about what this, in a previous video, about what this ticking update data structure is. Just as a reminder, it encapsulates a nice little snapshots of the table as it underwent all of the delta operations. So to be specific, it has a snapshot of the table before any mutations happened. It has another snapshot after the removes were applied, another snapshot after the adds were applied, and another snapshot after the modifies were applied. And you can kind of drill into it at any of those levels if you want to, if your app kind of needs that information, and kind of pick out the information you need. And so we're taking great advantage of that here, where, for example, in the modifies clause, we're taking the snapshot of the table before it was modified, and we're telling the library, hey, please print these rows indicated by the vector of row sequences called modified rows. And hey, print the table after the modifies given the vector of row sequences of modified rows. And just to be pedantic, you'll notice I was careful to say just now the vector of row sequences of modified rows, because in the modify case, you don't get a single row sequence with all the modifies. You get a row sequence for each column. The example I said before, column A might have modified rows 3, 4, and 5. Column B might have modified rows 10, 11, and 12. That's why this thing called modified rows is a vector of row sequences.
Hopefully also as a kind of like, trying to help build a mental model of how this works, right? Each one of these snapshots, and you see some of them here in the on tick callback, right? Update itself is the update, and before removes, before adds, before modifies, and after modifies, each one of those is like the full thing. So that's why when we're calling the print, we need to say print these particular rows in this update. So it may sound a little bit redundant in principle that the last line there, 145, it says update dot after modifies, and then we have to say update modify rows. Why do we need to specify which rows, right? Because not all of them potentially were modified, and that update has the update of the complete table after the modifiers are applied, not necessarily only the modifiers.
Yeah, that's a great point, and to just amplify it by that, if you were working with that particular snapshot by itself, that is a bona fide whole table, as Christian just said, and you could do anything you wanted to it. You could print the whole thing. You could pull data out of it. As I'm just repeating what Christian said here, but because our job here is to pick out the modified rows, we literally have to use the stream method and say, here's a table, and I only am interested right now in looking at the subset of rows indicated by modified rows.
And it's kind of like a good, this little method here, right? It's kind of like a good template to look at depending on what you need to code, right? Because as Corey was saying, depending on what the work that you want to do with the data is, maybe you only care about the end result, right? You don't care about what the data was before. You just care about this is the whole resulting table updated for you efficiently by Deephaven. Whatever rows change on the server side and whatever the server side efficiently communicated to you so that the client side state can update the table to reflect whatever the latest version is with just enough information for that delta you get as this last update, right? It's like the full result of the table. Now, if you need to somehow compare what changed because you're doing some operation and we're about to show you, and I think in previous installments we have done this, right? We're going to do this thing. We're going to keep an updating sum, and for the updating sum, the modify is going to essentially take advantage of knowing, oh, this value that we had went away, and this new value showed up. So we're going to be summing all the values in a column, and we're going to remove the previous and add the new. That's a kind of operation that requires this context for the modifiers, where just having the end result of the table is not enough, right? You cannot do your update with for an operation that requires that kind of state. But I think I'm running ahead of ourselves here. I should defer to Corey to ease us into that part.
So we're calling this process diffs. We're not doing a whole lot of processing, but we're looking for an excuse to do some processing on the client side. What we've decided to do is basically compute the sum of the int64 value column of this table. And if we look at this callback, we'll start by looking at the code. This code is also kind of comprehensive. It'll handle any kind of table, whether it's getting adds or removes or modifies. I don't know if I'll go line by line here, but basically you can see that the logic here is sort of like, oh, I'm going to process the removes clause first, and I'm going to pass a value to this process deltas routine of -1. And as you'll see when we look at that method, that'll be like the effect of subtracting out those rows because it has kind of a negative parity. And then I'm going to add the new rows, the added rows, and I'm going to add them in with a value of +1. That gives it kind of like a positive parity. And then things get a little more detailed with the modified rows. Basically, I have to, I've got a little cheat in here where I'm only looking for modifies in one column, namely the int64 value column. So I'm not processing and adding up all the modifiers. I kind of know what my call index is. And I'm pulling in that row sequence. And then I'm calling process deltas again, taking the table before the modifiers were applied, doing this thing with the -1 to kind of subtract them out, and then taking the other table snapshot after the modifiers are applied and applying it with a kind of positive parity. And so hopefully you can kind of see from a 100-foot view, kind of see what the logic is. And if we scroll down to process deltas, it's kind of not too bad. Basically, it takes one of these tables, selected out of the table update snapshot thing, and it takes a row sequence. It does this operation, which we've kind of seen before, using the Deephaven chunking operations. So using a sort of given chunk size, it makes a data buffer of that size, in this case 8K, and it has this simple loop where it uses these two methods, take and drop, to take slices out of the row sequence and process them a slice at a time. So these rows is the first up to 8K chunk of the row sequence. I say up to 8K because it might be smaller, and so then I figure out what it is here, and then I kind of drop them from the front and let rows be the sort of suffix, whatever rows might lie beyond those 8K. I use this fill chunk method to move data from the column source to my buffer. This is the source, this is the selected rows, this is the destination, and this has to do with the handling of nulls, whether you wanted a separate buffer of Booleans, which would indicate whether the kind of values are null or not. We don't care about that at the moment. But once I've filled my chunk, then I basically literally just add it up with this simple row here. I can treat my chunk like a C-style array. I multiply each value by the parity, and that gives you that +1, -1 trick.
The parity is essentially a way for the calling code to tell us, do we need to be taking this out or do we need to be adding this in, right?
Yeah, exactly.
A little commentary there, right? The structure of processing by chunks. We have talked about this before. There is some amount of complexity there, but we care about being performant. And since we do care about being performant, doing operations in batches is very, very important, right? It enables vectorization to actually do things for us, which can considerably increase the speed of our algorithms when we're processing lots of data. And that's what we're about. We're processing lots of data. And I mean, furthermore, we are using C++, right? So presumably we do care about performance. And this is part of the deal of caring about performance.
So now we run that process diffs method and give it our table name demo3. Here we go. And so you can see it's processing one modify per second, no adds or removes. And It's the current sum is about 11,395, 11,405. It kind of changes based on what's going on. And so, is that correct? Well, let's go ask the Deephaven server what it thinks the sum is.
Our sum in the C++ client side was increasing by 10, I think, which I mean makes sense, right? So that looks right.
Right. So I'm going to use my trusty, query that I use a lot, and hopefully we will see similar numbers. So 12,325. Click over here, and we're 12,345, 12,355, 65.
Looks good. And this is completely different calculation, right? Because on one hand, we have the client side computing this sum based on what's being changed on the table with messages that are flowing from the server. And on the other hand, we have the server itself calculating the sum on a derived table based on that table that is being sent to the client. But that derived table is not being sent anywhere. The client is not subscribing to it. We just have it for the purpose of comparing the two, right? So, I mean, our example here, you could say that it's a little bit artificial, and it totally is, right? We're creating this synthetic table on the server side for the purposes of being able to show client-side functionality in a very controlled way so that we can explain it, right? That we can calculate this very easily with the server itself to validate the data. Obviously shows that the right way to do this in Deephaven would be to calculate it in the server and then ship the result to the client. But the point of having a client that can process deltas is because presumably you have some code in the client side that you need to do things there that you cannot easily do in the server, right?
Yeah, you may be integrating with other code or other fancy financial libraries or other parts of your system where you're consolidating messages from various places. I mean, you might have a very complicated situation, and this is just meant to strip away all that complication and show you that the client can keep up with the server.
And on keeping up, we're going to show you an example where we do the same thing, but with a little bit more than 10 rows.
Okay, so in this next demo, we're going to generate a much larger table, one that creates about 1 million rows per second, and then we're going to show that the C++ client can handily keep up with that larger table. So on the server side here, I'm going to run this query, which is basically every microsecond, 1 million times per second. I'm going to add a new row where the in64 value column gets a new value, which is a random number between 0 and 999, just for readability's sake. And I'm going to keep the last 3 million of those. And so I'm going to do my import command, and then I'm going to run this query. And I'm also going to calculate the sum using this query that we've used before. And it's about 1.5 billion, give or take. I'm going to switch over to the C++ side. We'll run our code over here, and demo 3A. And we will hopefully see values on either side that match each other. So on the server side, I see number ending in 312. On the client side,
then 400. 312, then 400. Yeah, there you go.
Okay, great.
So we're matching. We went straight ahead to printing the sums and not print all the rows first because, 1 million rows is too many. So.
I want to do a similar demo, but you'll notice that this demo is similar to the ones we've done before. It is a table that's getting adds and removes. We wanted to do something similar with modifies. So let me quit my program here. Let me go back here.
Let's change the query of it, right?
Let's make a new query.
As it is right now, it is adds and modifies because we're keeping the last 3 million out of a table that is generating 1 million new rows at the end every second. So essentially, from the point of view of the changes that happens to the table every second, we have 1 million rows being added at the end, and the total 3 million means that the previous million scrolled up, like went away, and we have adds of 1 million, removes of 1 million, right?
All right. So in the next query, we are going to let's take our previous query and turn it into one that kind of does more, that causes modifies to happen by generating numbers and kind of bucketing them into various buckets. And so what I mean by that is I'll do this same calculation, but I'll add a new column, bucket equals II mod 1 million. I think I might cast it to long just to be on the safe side.
Then we don't need the tail anymore, right?
I'm going to do last by on bucket.
There we go.
And so hopefully, having typed this by hand, I don't know what's going to happen. But hopefully, when I run this, oh, look at that. We have the bucket numbers on the left. They should go up to 1,000,000 to 99999, and they should be kind of constantly changing, which is great. So as before,
we can do our sum.
And we have our numbers there. So back over here to the C++ code, demo 3M. The cool thing is we're seeing modifies, not adds or removes anymore. And then we'll go back and look over here, and we'll try to memorize these numbers. 375. Yeah, and you remember 474 was next? Yeah. Great. Perfect. So it works. Yay.
Great.
And
so we do the same thing with add and removes with the tail query, and now we're doing it with the bucketing for 1,000,000, and this is only modifies. One small, slightly pedantic, if you want, or if you are like, more generous, a little bit geeky of a comment, we're using this running sum algorithm as a way to figure out an example to show you something that is easy to understand on the client side, right? Is what we came up with. This running sum that we implemented, that Corey wrote in C++, is a perfectly good implementation for integer values. Please do not do such an algorithm, that simple-minded algorithm, for floating point values, for the float or double types, because it works terrible. There is something called numerical stability of algorithms, and that algorithm essentially taking a number that is very close to another number and then subtracting, that creates enough of an error in something that is done over and over and over that the error accumulates and your result can be very, very wrong. Okay, so I mean, just be aware. You don't need to dig into this or anything. The reason we do know in Deephaven is because we do have an operation on the server side that is a grouping sum that is prepackaged for you that you can use, right? And we learned the hard way that this is the case, and we had to develop code that was a little bit more aware of floating point and how to calculate a value with controlling the error associated to a running sum. So anyway, if you're curious, you can look at the search, but be aware, be careful.
All right.
Cool.
In our final example, we are going to show how to connect to a real data source, a real-world data source, a feed from CoinBase. We will show you that next. All right. So for our final example, we wanted to show you how we can use Deephaven to connect to real-life data and fetch data from the cloud and process it locally in the C++ client. And for that, I'm going to hand off control to Christian and have you show the demo that you've got lined up for us. So Christian, take it away.
Thank you, Corey. So what we wanted to do, right, is show you some real-life data that we're getting being published right now. And we have some examples in a separate repository in GitHub. We're going to use one of those repositories and essentially run a prepackaged application based on Deephaven that we already have there. And we're going to connect our C++ client to that prepackaged application. The application is actually using the CoinBase WebSocket API. That is a publicly available API. But that, as we were saying, it's already packaged for you in an example that you can run with a few lines of code. I'm going to click here and show you the repository where you can actually get the code for this. The way this application is actually packaged, we have several different ways that you can run the Deephaven server. And in one of the ways that you can run it, it actually runs inside a Python interpreter as a library. So essentially, you create a virtual Python environment and install one particular package. And when you do that, Deephaven will start inside your Python interpreter, and that will have a Deephaven server running inside. There are some instructions here that I have already followed. They are really short. With a couple of lines of code, you can get this thing up and running. We're not going to do that in this demo.
you have to assume that I already follow those instructions and I have a locally already installed Python environment. So I'm going to switch to my command line tab here. This is my machine. I have installed, I typically use the py directory in my home for my Python environment, and I have a Deephaven DH directory inside where I have installed that particular environment for that application. Okay, so the thing that I'm going to do is that I'm going to activate the environment. This is the typical way that you activate a Python environment. And now I'm going to go back here and essentially take the actual command that we need to run. We're telling Python to run with our application, right? The Deephaven _example app. When I do that, actually, I'm going to be starting a Deephaven server underneath. And it prints server started on port 10,000, that same port that we're used to. So now that we have the Deephaven server running, I'm going to go to our typical address that we're used to for running the web ID, same port, 10,000. And now we see the application, okay? Essentially, this application is creating two tables, the matches table and the matches stats. The matches table are the executions happening right now in CoinBase for two particular products. We're just subscribing to two products, okay? We're not getting every possible product being traded in Coinbase right now. We're just getting the two major ones, the ones that trade the most. Those are Ethereum, ETH-USD, and Bitcoin, BTC-USD. And you can see this table is essentially growing at the top. The timestamps are moving. This happens to be the current time, is October 24th, 18:40 p.m. So these executions are happening as we speak. This is live data. The stats table gives you some statistics about the totals executed, but we're going to concentrate on the individual list of transactions for what we want to show you, okay? So we want to we have a stats table, we have a matches _stats table that gives you some statistics about the totals executed for each product, but we're going to concentrate on this table, the one that shows execution, that is called matches table. The word matches there is kind of interesting. It has to do with how these trading applications typically work. You have orders that are addressed and orders that became active, and they are trying to match regarding their price and sizes. And when you have a match that creates an execution, the details of that, depending on how familiar you are with these automated trading applications, may be a little bit complicated. What we want to understand from the point of view of looking at this data is that each individual row is one execution. Essentially, somebody bought and somebody sold a certain number of shares at a certain price. One little caveat, the first time you run this application, it may look a little bit different to you. I have it run it in the past at least once. So I have some cached state for my panels in the local cache in my Chrome browser for this machine. When you start it the first time, you may not see any tables. You need to go here in panels, and you have the two tables here. When you click on them, you will see the actual tabs for the tables showing up, okay? If you see this empty the first time you run this, don't panic, it's not wrong. Just go to panels and click the right one. Okay, cool. So what we want to do now is it's a very simple first run of the same program that we used in our demo a minute ago. And we're going to use that program to essentially capture the table and show the deltas. If you remember, we first show you the full table in the states when the client joins as ads, because that's the first barrage method that shows up. And then after that, we show you this. Before this point, we were playing with canned data. We had timetables inside the server generating data for us. This is actually real live data. That's the main difference, right? We're going to be essentially looking at the same functionality, but for a different data source. One happens to be live. So I'm going to go here to another command line that I have open, just like, to keep accounting, right? I am still running my Python interpreter that has Deephaven server inside, which is essentially providing me with the server side for this view that I have in this window. Now I'm going to have another window here, and I'm going to go to my checkout of the C++ client code where I already have everything built, and I'm going to run the same binary that so far Corey has been running inside his IDE for the demo that we have had so far in this installment. So I'm going to go to DH. I call my checkout, my clone OSS1. Inside OSS1, we have Deephaven core. Here we have CPP examples. And inside examples, we need to go to demos. And inside demos, we have chapter 1, chapter 2, chapter 3. We are in chapter 3 now. They are built inside the build directory, and I'm going to run chapter 3. When I run chapter 3, we have our input technology that Corey has shown in the past, and I'm going to say option 2, which is print diffs with library, okay? If you remember, our option 3 there has some hard-coded column names that we don't want to be using right now because these tables don't happen to have the same column names that we have been showing you. So I'm going to use option 2. And I need to provide the same table name that I have in the application for the one table that I want to show. So since I'm going back here, let's say matches underscore table and press enter. And we have the first dump. And now we have the deltas. And the deltas happen to be adds because this table is growing. It's adding more rows. We have it here. It's running, right? There's a C++ client. It's receiving live data from the Deephaven server. We wanted to show you something more realistic, some real data source that anybody can get to. You can play with this on your own. You can follow the instructions in that examples repository to install. It's very easy, it's just 4 lines of code. And then if you build a C++ client, you can do this and maybe play a little bit with it.
And I think, if you were, the vision here, or the imagination is that if you were a Bitcoin trader or be able to look at this data and then feed it into your custom algorithm, whatever the case might be, and perhaps do some analysis on live crypto data coming from Coinbase. Right. So you could take this data and do your own kind of custom analyses on it. Just as a first step, if you wanted to make it look like our previous demos, you could modify the C++ code in the style that we've done already for our previous examples. You might, for example, make a new Deephaven derived table which groups these transactions by product ID. Or, as another example, you could take this live data and just do a last by the product ID. So you could say, I only want to see the last Bitcoin trade or the last Ethereum trade, and I want to do some kind of analysis based on that. The point is that the C++ client gives you, access to all this data, and you can operate it locally in your C++ code and do kind of whatever makes sense for your application.
Another example could be you typically care on what volume is being moved per unit of time. At some points in time, products are kind of like quiet, they trade a little bit, but then when the price begins moving, people rush to either get in or get out, and you get like a lot of volume being executed, like the size. So it's typically interesting to look at number of shares per unit of time, like per minute. So what size per minute is being executed, right? So you could have some very simple-minded application that is calculating some speed of trading metric, right? And it triggers an alert, right? You want to know if more than X volume is being traded per minute, maybe you need to pay attention because you have some Bitcoin investment and you want to know that something is happening in the market right now and you don't want to be left behind without figuring out that the price is moving under your position, for example.
That makes sense. And maybe we'll close for now. Hopefully, we've given you a sense in this video series on how to program in C++ against the Deephaven server and get data from it and process it, and even connect to, as we've done here, connect to live ticking data out there in the real world.
And best of luck in your Deephaven real-time data endeavors.
So thank you for watching this video. To summarize, we learned about how to process modifies from the server, and we also showed the client staying in sync with the server for a more high volume application, in this case, 1 million rows per second, dealing with adds, removes, and also modifies at a rate of 1 million rows per second, and then kind of the C++ client keeping up with the server. And we also saw a real world application, seeing the C++ client connecting to Coinbase. So that's the end of our video series for the C++ client. Thank you very much for listening.
Very good luck with all your Deephaven endeavors and C++ client endeavors.
All right. Thank you.
Guys.
Thank you and good night.